one was 1 kilograms. That's for the LPG. What was the quantity for the crude oil?
On there, it's 1.53, and then the crude oil is 5.120. Sorry, 5.20. 5.20.
Oh. Okay. Like this, right?
Oh, yes, yes. And then 5 point.
And then 5 point what?
20.
20.
Yes.
Okay,
yes.
you remember after the decimal point, we don't call numbers by their names. We call them digits, by the digits. Okay. All right. So this is what we have. 1.53 divided by 5.20 times 100 over 1. So this whatever is the answer to this would be our final answer. Now, in these exams, they will let you use a calculator, right?
Yes.
Okay. All right. So go ahead and get this done on a calculator. Let's see. So if I were doing this, I would either say 1.53 times 100 divided by 5.20. I would get the answer. Okay. So what did you get?
29.42. But it says to 3 significant figures, so 29.4.
Okay, so that's 29.4, right?
Yeah.
Okay, so we'll go with 29.4%. Okay, the answer would be percentage, like that. Okay, so I think we can proceed, right?
Yes.
Okay, so I'm going to stop sharing so you can continue. All right, you can proceed. Go ahead and share. Okay, I can see your screen now. So you just need to navigate to the question paper. Okay, nice. Okay, so okay, this is the next question. It says gases in the Earth's early atmosphere caused changes on the Earth. Draw one line from each change to the gas that caused the change. Ooh, okay. This one is let's see. So how were the oceans formed? Okay. The gas that caused the change. I'm not too sure about this one. I think we should just save time. Let's go to the marking scheme. Okay, sedimentary rocks, I'm not too sure of it. But what does the marking scheme say?
Sedimentary rocks is to carbon dioxide. And oceans formed.
Okay. And which one? Yeah.
Water vapor.
Okay. Interesting. Okay. Carbon dioxide and water vapor. Okay. Okay. This one looks like another calculation thing. It says table 1 shows the percentage of some gases in the atmospheres of Earth and Mars today. Okay. Okay, so that's like a side-by-side comparison. Let's see what they say. Which gas has the highest percentage in the Earth's atmosphere? Okay, so from what we can see, I think it's safe to say that it's nitrogen, right? Hold on. 1 minute. Hold on a minute. I think, yes, it's safe to say it's nitrogen, yes. It's nitrogen, that's correct. Okay. So, what's the next question? It says calculate how many times more carbon dioxide there is in the atmosphere of Mars than in the atmosphere of the Earth. How many times more? Okay, so that means basically we're comparing. So if we look at this table, carbon dioxide on Mars is 95, while on Earth it's 0.04. So if that, of course, obviously on Mars it's more on Mars than it is on Earth. So the whole idea is how many times is 0.4 going to be multiplied by to give us 95? Basically, all you need to do is to divide 95 by what? 0.04. That's all. So um, another way we could say it is if we can say 95 divided by 0.04. Okay. So what did you get? Let me see if I can open my.
Two
What did you get?
2,375.
2000. Wow, that's a huge number. Okay, but yeah, if that's it, then that's it. Let me just confirm it. So I'm dividing 95 by 0.04. 95 divided by 0.04. Okay, yeah, it's exactly 2,375 times. So yes, that's correct. Okay, it says it should give your answer in standard form. So can you turn that to standard form?
Times it by 10 cubed.
Yes, yes. Are you familiar? Are you really good with standard form?
Yeah.
Okay, so what would this answer be in standard form if you were to convert it to standard form?
2.375 times 10 cubed.
Yeah. 10 raised to power what?
Power of 3.
3, right?
Yes.
Okay, yes, that would be 3 because that's the number of times your decimal point will need to move to the right-hand side to make it back the original number, correct? Okay, so that's it in standard form. Okay, let's move on to the next question. So sorry, before we move on, do they agree with the answers that we've gotten so far?
Um,
The answers on this one.
yeah, so nitrogen, and then
Do
yeah,
they
2.
agree? Just confirm it.
Yeah.
Oh, okay. Okay. Okay, perfect. Okay, let's move on then. Let's move on. Okay, this one is the graph. Let's see what's up with this graph. It says, um, how is the concentration of carbon dioxide in the Earth's atmosphere changed from how has it changed? Sorry, how has it changed from 1960 to 2020? It has increased. I mean, from a graph that's tilting this way, that's an increase. Okay. Do you remember when we talked about those kind of the different ways a graph could slope? It could slope like now. This one is sloping like a positive slope, and you could also have a negative slope where imagine it was sloping downwards from 450 to say 300 in 2020. Okay, so that would be a reduction or a deduction rather. So the decrement, let me just use that word. So in this case, it's increased. But let me just ask, just for clarity, how do you think the graph would look if it stayed the same or if it increased? So I'm going to quickly just share this because I guess that this is just basically testing your knowledge of how graphs look. Just 1 minute, please. Okay. Should have used an existing whiteboard. Why did I not use that? Okay. So it's loading. So do you have an idea of, did you get the question I asked?
Yeah, how would it look if it was decreasing or stayed the same?
Yes. How would it look? So I just want to sketch something for you. Looks like this whiteboard thing is really cancel. Just 1 minute, please. Let me see if I can just launch PowerPoint and use it. PowerPoint.
I
But
should
it's
stop
just that
skipping.
PowerPoint is going to be a bit heavy. But let's see if I have a draw somewhere here. Yeah, I think I do. Yes, just 1 minute, please. I want to see if I have a draw tool here. Nope, there isn't a draw tool. Okay, no problem. Okay, you said you can what do you call it? Let me see. I think I can even annotate. Let me see. I should be able to annotate. Yeah, just remember that. Annotate. Enter. Okay, just give me a sketch. Show me how you think the graph would. Okay, can you hear me now?
Oh, yes, I can.
Okay, all right. My internet wants to act up. Let me see if I can have something standing by. Okay, so go ahead and share. Are you sharing, Noah?
Yes.
Okay, okay, I can see it now. Yes, perfect. Okay. All right. So can you annotate? Just show me how you think the graph would look if it was decreasing. So we have established that it's increasing. Yes. Oh, nice, nice, nice. Yes, correct. Okay, okay. Then what would happen if it stayed the same? How would it look if it stayed the same from 1960 to 2020? Oh, perfect. Yes, correct. Okay, that's good. Okay, don't worry. You can okay, let's move on. Let's move on. I just wanted to be sure. That's fine. You're good with that. Let's move on. All right. So cars emit carbon dioxide. Okay. Okay. It says a car emits 17.2 kilograms of carbon dioxide on a journey. There were 4 people in the car. Calculate the mass of carbon dioxide emitted per person. So, because I really wanted to um, establish this. Is it really, when they say a car emits this, right? I think it's to be more specific, it's the people in the car who are actually giving off carbon dioxide, not the car itself. technically cars, the gases that they emit would be somewhat around carbon monoxide. Okay, but we'll leave that for maybe another question that may feature it. Okay, so what do you think we'll do in this scenario? What do you think we'll do to find what one person emits?
Divided by 4.
Yeah, divided by 4. So go ahead and do that. Let's see what you have. If I do 4, okay, let's just do a mental calculation. 4 in 17 is 4, remainder 1, isn't it?
Oh, okay, yeah.
Yeah, and then 4 in 12 is 3. So that's going to be 4.3 kilograms. So um, if we were to find out the mass emitted by one person, then that would be 4.3 kilograms. Now, I'm sure you remember back then when you were still in Nigeria, when I said uh, you would really be fast with these questions if you could do as few as possible on, with writing. If you could do more mentally, you would find that you'd be faster. So always aim for that. Let's see how fast you can push your speed so you can get more questions correctly. Okay, so you got that right?
Oh, yes.
Okay. All right. And the marking scheme agrees.
Yes.
Okay. Let's move on. Planting trees helps to reduce climate change. Okay. Why? Because trees use carbon dioxide from the Earth's atmosphere. Okay. I think we've established this fact that trees use the carbon dioxide that we give out. Okay. And that carbon dioxide is also in the atmosphere. So it takes out the carbon dioxide from the atmosphere. It says name the process in trees which uses carbon dioxide. Okay. This one is a pretty simple one. What's the name of the process?
Photosynthesis.
Exactly. It's photosynthesis, where it takes up the carbon dioxide, combines it with water, and in the presence of chlorophyll to form glucose or carbohydrate. That's the food or starch for itself. Okay. All right, we move on. It says, this is a graph. Okay. 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 Annual change in forest area in arbitrary units. Okay. It says we should give 2 conclusions about the annual change in forest area. Okay. It seems to me like in Africa, we had an increase. Okay. In Asia, we had like a decrease. In Europe, we had an increase, but not as much as in Africa. And while in South America, we had a decrease. So if I were to look at this, I would say the activities, commercial activities, cutting down trees and stuff like that, that happened in South America was way more than that, what happened in Asia, okay? Whereas for Europe and Africa, we can conclude that uh, there was more, um, should I say, there was an increase in vegetation, or I don't know, tree planting activities by either people or by animals, animals just propagating seeds carrying seeds from one point to another. So uh, yes, that's what I would say. If I were to do this, I think it's safe to compare Asia and South America, and then to compare Europe and Africa. since those ones are on the positive side. Okay. So for that first side, I think you can choose anyone you want to start with. You could choose to compare Asia and South America. How? Asia and for South America, we had a greater decrease in forest area, okay? A greater decrease in forest area than in Asia. And this is usually due to commercial activities, cutting down trees for timber and other uses in those areas. Whereas for Europe and Africa, we see there's a kind of an increase, but there's a higher increase in Africa than there is in Europe. Most likely, again, because of more areas in Africa would still be populated by animals, and then these animals help to propagate those plants. Okay, so yeah, I think that's how it compared. But let's see, what does the scheme say?
It just says compare the decrease and increase between Africa and South America, or between Europe and Asia.
Okay, okay. So they compared the ones that decreased, right?
Yeah.
Okay, and then compare the ones that increased, isn't it?
Yeah.
Okay, okay, no problem. Okay, that's fine. I think in that case, then they agree with us. We can move on then. Okay, so we come across methane. Methane is a greenhouse gas. Figure 3 shows sources of methane emissions. Landfill, okay, natural sources, 29%. Fossil fuels, that's petrol and the rest. Okay, burning of fossil fuels is 19%. Other sources is 46%. It says determine the percentage of methane emissions from landfill. So how would you calculate this? Can you guess?
Just add them together.
Yes, you add them together and do what?
Subtracted by 100.
Yes, yes, exactly. Because it's percentage, correct? Okay, that's correct. I think I'll go with that. So let me just ask this, just for fun. If the unit was in degrees, okay? Now I'm not that I'm expecting it, but let's just say they decided to play, they wanted to play some games with this question, and they used degrees instead of percentage. What would you do to find out what landfill would be?
They put in degrees.
Yes.
360.
Okay. So yes, what did you say?
It would add up to 360.
Yes, correct. That's it. That's exactly that's what it is. So just like you said, 29 plus 19 plus 46, then subtract their sum from 100. In that case, you'd now be adding whatever it is for natural plus whatever it is for fossil, and then whatever it is for the other sources, and then subtracting it from 360 degrees to give you the degrees for landfill. Yes, that's exactly what it would be. Okay. All right. So yeah, we can move on. Or okay, I guess they have a value there. So it's just basic subtraction. I think we can move on. Okay. Figure 4 shows two ways, A and B, of preventing used items going to landfill. Okay, of course, that's recycling. I mean, that's obvious. So the first one says name A and B. Choose answers from the box. Um, okay. So, of course, A looks to me like we're recycling. Okay. So 2 ways of preventing used items from going to landfill. Okay, so should I go with recycling for A? Because B looks like, so if you use it, make it, use it, dispose it, and use it to make something else. Okay. Okay, so you know what? I'll say B is recycling. A, we don't need to dispose it. We
Oh,
just use it and
so it is
use it
also
and
reuse.
reuse it. Okay, so A is reuse. Yes. A is reuse. Yes. I'll go with reuse for A, then recycle for B. Okay. So can you see the difference?
Yeah, yeah.
Okay. So if I were to just give an example, right? Imagine you have a Coke bottle, right? So the first time you took the Coke from it, you are done with it, and then you decided, oh, I'm not going to dispose it. I'll use it for storing water, right? That would be an instance of A, because you you know it was made, you used it, and then you kept on using it, you didn't throw it away. Okay, that's an example of A. But an example of B would be, okay, so you bought the Coke bottle, you bought the bottle of, you drank it, you thought of, okay, maybe we should just dispose it. And then after disposing it, landfill, you either away that to some drainage and therefore land. But you did someone and decided, wow, but that was after it was disposed. Okay. So once come up with the use that Coke bottle for something else, then so you can just say that the basic difference between recycling and reuse.
Hello.
Okay. So no, I'm still there.
Yeah, you're just your
Hello.
yeah, your voice is very laggy.
Did did you understand my okay. Okay. Okay, but can you hear me clearly now?
Yeah, yeah, I can hear you now.
So I was just saying that the difference between reuse and recycle is that in the case of reuse, you wouldn't need to dispose anything. For recycle, it would involve disposing it first and then someone using it for something different. Okay. So the marking scheme agrees on that, right?
Yeah, yeah, yeah.
Okay, all right. So can we proceed now? Okay. So this is dealing with, what's it called? Water. Sample of water being heated, evaporating basin. Okay, this is the method used for this. It looks like an experiment. Okay. Weight, weigh an evaporating basin. Okay. Add the sample of distilled water to the evaporating basin. What next? Weigh it again and the water sample. Heat the water sample. Weigh the evaporating basin and contents. Repeat steps 1 to 5 two more times. Repeat steps 1 to 6 with seawater. Okay, so this is an experiment, right?
Yes.
Now I want you to imagine what we're dealing with. We're dealing with gas because that's what is going to produce the heat for us. Okay, so let's just imagine we're in a lab, a chemistry lab somewhere, right? So what are the precautions? What safety precautions would the student who participated in this experiment take? Just one of them, or let's just mention a couple of them that come to mind. Remember, we're dealing with heat. So what do you think he should do as a safety precaution?
With heat,
Especially, yes, go ahead.
gloves.
Good, gloves, yes, to avoid burns, correct. Any other one that comes to mind?
Wear glasses.
Yes, because by the time the water would start boiling, hmm, that could cause the water to, splash, and you will not like it getting close to his eyes. What else would one? Okay, they only want one, so we gave them two. Okay, any other one we might have overlooked that the marking scheme mentioned?
Um, it says wear safety glasses, goggles, and tie hair back.
Okay, and do what?
Tie hair.
Oh, okay. Yes. Because of the possibility. Remember, we're talking about possibly flames there because we'll probably be using a Bunsen burner. So yes, tying hair back would also be an important precaution, especially if the person has long hair. Okay, that's fine. Okay, let's move on. Okay, so it says the method used did not give valid results. Okay, so let's see. Which two improvements could the students make to give valid results? Tick two boxes. Let's see. Heat until the mass of the evaporating basin and contents does not change. Is that possible? Leave some water in the evaporating basin after heating. Um, Record the results in a table and plot a bar graph. Use 25 cubic centimeter of water for each experiment. Use a beaker instead of an evaporating basin. Okay, so to uh, to to attend to this question, I think I would go with the second to the last one. Use 25 cubic centimeter of water for each experiment. Why? Because you are more specific about the amount of water you're using. So let's even imagine, what are we trying, what do you think this experiment is trying to do without being told? We're using water, distilled water and seawater. So most likely we're testing the effect of salt. This, seawater contains salt, right?
Oh yeah.
Uh-huh. So we're testing the effect of an impurity on the boiling point of water. Most likely, you understand, I'm just trying to um, um, uh, guess what the experiment will be talking about. We're testing the effect of an impurity on the boiling point of water, and we're expecting the boiling point of water to increase. So normally the boiling point of pure water should be 100 degrees Celsius. But now imagine it's seawater or water that contains salt. There's no way it can be 100 anymore. But if we are not, we don't have any amount of water to use to measure it, then, we might not be able to really gauge, um, we might not be able to gauge, uh, uh, or come to a sound conclusion. So I'll go with that second to the last one. And maybe, let's see, record the results in a table and plot a bar graph. Okay. 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 Yes. I think I'll go with those two. Recording the results in a table and using a given amount of water for each experiment.
It says
Okay. What did they say back there?
heating until the mass of the evaporating basin and contents does not change.
Does not change. Okay. That's the first one, right?
Yeah, and the second one is use 25 centimeters cubed as
Oh,
water.
okay. 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 So they agreed with us on one instance. Okay, to heat until the mass of the evaporating basin and content does not change. Let me see. Okay. Okay, I think it makes sense. So the idea is that if you heat seawater and there's salt in it, right? Um, all the water would leave and leave the salt in it. So So I think there's some sense in it to heat it until the mass of the evaporating basin and the contents does not change. Okay, okay, okay. I think it makes sense. It makes sense. That way you would know if all the water has evaporated. And like we said, we're testing the boiling point of water. Okay, all right. Okay, that's fine. So yes, that's the correct thing. The first one and the one that is more specific about the volume of water. Okay, yeah, we can move on. A different student used a method which gave valid results. Okay, so let's look at the results that student gave. You want to scroll down?
Sorry.
Yeah. Okay. So let's see. Okay, that's it. Type of water, distilled water, seawater, mass of dissolved solids in grams. Okay. Distilled water obviously doesn't have anything dissolved in it. Seawater does have salt in it, so we know. The student concludes that distilled water is pure. Suggest one reason why. Based on what I just explained now, what do you think would be the reason why he could conclude that distilled water is pure?
All of the tests are equal. I mean, give the same results. Yeah.
I didn't get that. What did you say?
All of their tests give the same result.
Okay, okay. Yes, that's showing us that there's no solid dissolved in it, right?
Yes.
Yes. Another reason would be that, well, okay, okay, fine. We cannot really say from here. But yes, pure water boils at 100 degrees Celsius. But anyway, since it's not mentioned here, let's not make any assumptions. Okay, let's scroll down. Let's move on. Okay. Uh-huh. Tap water is potable. One step in producing potable water is sterilization. Why is potable water sterilized? Why? Of course, it's to kill bacteria. There's nothing else. You can't. It's not. It's not. You're not removing any dissolved solids. Neither are you improving the taste. It's to kill bacteria. That's it, basically. It's more like to purify it. Okay, we're good with that one, right?
Yeah.
Let's move on. Chlorine is used to sterilize water. The reaction between chlorine and water is reversible. True. Complete the sentence. Equilibrium is reached when the forward and reverse reactions occur at the same rate, uh, speed, sorry, yeah. They occur at the same speed or the rate of the reactivity. Okay, so what does the marking scheme say there, where equilibrium is reached? Hello, Noah, are you there?
Yeah.
What does the marking scheme say for that question?
Rate.
It's rate, right?
Yeah.
Okay, no problem. And rate refers to speed, okay, in its own way too. That's reactivity. Okay, let's move on. The test for chlorine uses damp litmus paper. Complete the sentence. Choose the answer from the box. When damp litmus paper is put into chlorine gas, the litmus paper turns is put into chlorine gas. Okay, I'm not too sure of this one. Is it green? I'm not too sure. What does it say for that one?
It says white.
White. Okay. Damp litmus paper. Okay. Sounds white. Oh yeah, chlorine. I remember chlorine is usually used like a bleaching agent. So sometimes it removes the color from stuff. It removes the color from things. So yeah, it makes sense. Okay.
Recording in progress.
Okay.
Okay.
What does this one say?
What does this one say? What does this one say? What does it say?
Okay. Um, there's evidence that adding fluoride ions into drinking water reduces tooth decay. It shows the percentage of people showing tooth decay. Okay. Water with fluoride ions, water without fluoride ions. Okay. Yeah. So what does it say? Compare the effect of adding fluoride ions to drinking water on tooth decay in people between the ages of 25 and 74. Okay. So what can we safely say on this? What would you say on based on this?
Um. hmm, Okay. So
Hello, Noah.
yeah. Hello. Yeah. Yeah. I'm here.
Noah, are you there?
So the
Can you
flu- the fluoride reduces um the decay. Hello.
Can you hear me?
Yeah, I can hear you now. I can hear you. I said the fluoride reduces the decay.
Okay. Yes. There's a reduction, but do you think there's a particular there's something we can say about the reduction, because it looks like the reduction is more clearer in people between 55 and 64.
Oh yeah, yeah.
Did you know? So yes, there's a there's a higher reduction there. Okay. Okay. All right. I think we can move on. What does the marking scheme say? Does it say anything there?
Could be a risk. Could be a risk to health. Could have side effects. Could discolor teeth.
Oh, okay. 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 It's talking about, I think it's into experiments now. A catalyst is used to increase the rate of decomposition of hydrogen peroxide. Okay. Hydrogen peroxide decomposes to produce water and oxygen. Yes. Write a word equation for the reaction. Okay. All right. So, do you want to give it a shot? Let's see. Can you think about what's happening here? When they tell you something decomposes, what comes to mind?
Decomposition.
Yes, decomposition. What's happening? What's the basic thing that's happening in decomposition?
The reaction is breaking down.
Yes, something is being broken down. So something is whole. That's where the reaction starts. The thing that is whole now gets broken down. So on the left-hand side of that arrow, right, we're going to have hydrogen peroxide. You write hydrogen, that's if you are writing it, of course, you write hydrogen peroxide there. Since it's a word equation they asked for, they didn't ask for a chemical equation. So you write hydrogen peroxide, then on the right-hand side, where you have the two spaces separated by the plus sign, you would have water and oxygen. Water on the left-hand side of the plus sign and oxygen on the right-hand side. Simple. Okay?
Oh, okay.
Yes. So remember, decomposition involves something breaking down. So you are not expecting to have two things on the left-hand side of that arrow. Okay, that's what you need to note. Okay. So let's proceed. It says a student investigated the rate of decomposition of hydrogen peroxide using 3 different catalysts: manganese dioxide, copper oxide, and zinc oxide. Figure 7 shows the apparatus that he used. Okay, so what's the question on that? It says this is the method used. Okay. It says which two control measures are used in the investigation. Okay, so
two control measures. Control measures are things that, let me see, I'm trying to remember now. Things that help us to vary the reaction, okay, so that we can come to conclusions using different aspects of that thing. So that's a control. So let's look at the things that changed here. Control variables. What are the things that changed? Um, measure this, add this, attach a gas range, no? Measure the volume of oxygen produced every 20 seconds for 120 seconds. Okay. So I think I'll go with volume of oxygen produced and now I'm not going, the first one there says mass of catalyst. We can't go with that because catalysts are designed not to get involved in a reaction. They only speed up the reaction, but they don't get involved in it. So the mass is not something that we would be looking out for. So I'll go with the volume of oxygen produced and the volume of hydrogen peroxide.
Okay.
Okay. Says what did the marking scheme say back there?
Mass of catalyst and volume of hydrogen peroxide solution.
Okay, hold on, let me see. Let me be sure. For control measures are, let me be sure of control measures in a reaction. Okay. Just a minute. I'm checking. Control measures in an experiment. Okay, in an experiment, control measures are techniques used to isolate the effect of the independent variable on the dependent variable. Okay. Okay, hello.
Oh, yes, hello.
Okay. So yes, I think that would be correct. The mass of catalyst would be a control measure since it doesn't get involved in the reaction. Control measures try to minimize the effect of independent variables on the dependent variables in an experiment. So yes, in that sense, yes, the scheme would be right. Okay.
Oh no, this one you need the actual paper.
Okay, to draw it, right?
Yeah.
Okay. Hmm. Okay. What does this one say? It says, which is the best catalyst? Give one reason for your answer. Okay, I'm not too sure of this. What does the marking scheme say about it?
Magnesium dioxide.
Okay. So what's the reason for it?
Steepest curve, reaction finish first, greatest volume of oxygen.
Okay, it releases the greatest volume of oxygen, right?
Yes.
Okay, and the reaction finishes first.
Yes.
Okay. 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 Let's see. Okay. It says that the student repeated the investigation with manganese dioxide catalyst. The results were all close to the true value. Complete the sentence. It says results that are close to the true value are okay, accurate, approximate, random. I think it's safe to go with approximate. As long as it's not exactly the true value, then it's approximate, isn't it?
Um,
Does the scheme say otherwise?
it says accurate.
Accurate. If it's okay, as close, they are close to the true value. Okay. The results were all close to the true value. Okay. If it says it's accurate, then it's probably as close as it could be. Okay, that's fine. So there are measures of closeness now. It's accurate. That's fine. Okay, let's go with that. But obviously, random is out of the picture because random is just, going anyhow. That would not be the answer. The student repeated the investigation using manganese dioxide catalyst at a higher temperature. What does it say? At a higher temperature, the rate of reaction will. Do you think temperature would affect this reaction? I'm not sure. I don't think it will. The rate of reaction is not affected by the temperature. Does it stay the same?
Um, say it will increase.
It will increase.
Okay.
Okay.
Yeah, yes, it says increase.
It increase. Okay. Okay. So the temperature affects it positively. Okay. Okay. What's the next one says? Methane is if you balance the equation. Okay, so can you do this? Can you balance it?
Okay.
Remember, when you're balancing, count how many atoms of each element are on the left-hand side of the arrow and on the right-hand side of the arrow.
Okay, so firstly,
You can see H, right?
yeah.
Yeah.
So firstly, I see the H on this side has 4 and the other one has 2.
Mm-hmm.
So that's changed to there'll be a 2 in front of the H2.
Okay. Yes. So that will make H to be 4, right?
Yes.
Okay. So now let's try and balance oxygen. Oxygen on the left side is 2 for now. Oxygen on the right hand side is how many?
4.
Yes, correct. 4. Because that's what you put in front to balance the hydrogen. So it's 4. So what should we do to the left to make the left come up to the right?
Add a 2 in front of the 0. I mean, oh, sorry.
Yes, in front of the oxygen, yes. And that will balance it, yes. Did you notice that we didn't need to touch the carbon? The carbon was already balanced, isn't it?
Yeah.
Exactly. So to balance this, just put a 2 in front of the oxygen, the O2, and put a 2 in front of the water. That's good. Okay. All right. Let's go on to the next one. It says how many no matter how pure it is, it's still a mixture of hydrocarbons. What does it say? Table 4 shows properties of petrol and diesel. Okay. Range of the number of carbon atoms in a hydrocarbon molecule, 4 to 12. And then for diesel, you have 12 to 20. Range of boiling points in degrees Celsius, 40 to 205. And then for diesel, you have 250 to 350. What does it say? Compare the properties of petrol and diesel. Okay. Well, it's quite clear that petrol doesn't have as many carbon atoms in a single hydrocarbon molecule as diesel has, right?
Yes.
So what does that tell you? Do you remember when we talked about cracking?
About tracking?
No, cracking, as in C, cracking. When we talked about cracking of petroleum substances. So what would happen is that imagine the boiling point for petrol versus the boiling point for diesel. Because you have more carbon atoms in diesel than you have in petrol, obviously the boiling point would be higher, right? Because more energy will be required to break the bonds between them. You understand what I'm saying, right?
Yes.
Okay. So So yes. So I think, yeah, if you want to, you can just compare it based on the boiling point. You have more covalent bonds. Hence, higher temperature, more heat will be required to break the bonds between the molecules. Okay. Well, what else does the marking scheme say?
Hydrocarbon molecules in petrol have fewer carbon atoms than those in diesel.
Okay.
Petrol has a lower boiling point than diesel.
Okay. Does it say why? Does it give any explanations?
Petrol is more flammable than diesel. Petrol is less
Yeah.
vicious.
Did you say petrol is more what? Volatile. Did you say volatile?
Vicious.
Oh, okay. That vicious is the what do you call it? That feeling that of friction in liquids, right? Friction in liquids, like, and it almost shows up as the texture. So yes. Okay, what does it say? Does it talk about the volatility?
No, it doesn't.
It doesn't. Okay. Which one is more volatile? Okay. All right. So yeah, I think we can move on. But one more thing we can say about petrol is that it can easily become, it's easier for petrol to become a gas than for diesel to become a gas. If you were to, leave petrol open, like in an open container, and diesel too open, and you come back, say, after a long period, extended period of time, to check the petrol and diesel, you would notice that the petrol has reduced more in um, quantity than the diesel. Boiling point, 2 degrees. Imagine 4 degrees. 2 degrees, it's not too far from each other. It can technically. Yes. Let's move on. It says the gas of carbon monoxide, of course. Yes, I think we've said that that cars will release carbon monoxide from the exhaust pipe. Then what next? Water vapor too. It says, which chemical element do all these gases contain? All right. So what do you think is the one common thing that all of them contain?
Oxygen.
Oxygen, correct. Now, somebody may not see it clearly, but if you look very well, oxides of nitrogen must definitely contain oxygen. That's what makes them an oxide. Carbon monoxide, the oxide in it again makes it an oxide. And even though we don't see oxygen in the name water vapor, we know water is H2O. So it's obviously oxygen that's in all of them. Okay, good one. Let's move on. It says, when diesel burns in car engines, oxides of nitrogen are produced. Where does the nitrogen come from? Where does the nitrogen come from? Okay. So, if we remember that the process of creating, of breaking, of getting diesel, petroleum products from crude oil is called fractional distillation, right? And it involves burning, heating up crude oil to a very high temperature in the presence of air. So I think it's okay. It's safe to say that the nitrogen would come from the atmosphere, from the air where the fractional distillation happened. But okay, that's my own that's my own conclusion. But what does the marking scheme say?
It says air.
From air, right?
Yeah.
Okay, exactly. So it's from the air. Okay, but it didn't say where it happened, right? If it was at the stage of fractional distillation.
No, it just says allow from the atmosphere or from volcanoes.
Okay, okay. All right, let's move on then. It says when diesel burns, another one, particles. What's that? Sorry. Okay, particulates may be produced. Okay, that's like solid stuff, little solid stuff. And it says what environmental effect do particulates from burning diesel cause? Hmm. Um. So, have you ever seen a diesel generator before, where it's, you know, um, when maybe it's been turned on, maybe just the first time, just turning it on. Have you noticed the fumes that come out from the exhaust that first time, and even subsequent times? So there are some that, from the moment you turn on the generator, those ones that can stay all night. Have you ever noticed the fumes that come out from the exhaust pipe?
Yeah. Okay. Yeah.
Those black fumes, I don't want to call them soot, but well, that's the closest thing they are like. They're just like soot in a way. Those things are pollutants. I don't know how else to describe it, but there's no other environmental effects they cause other than choking. That they have a choking effect, and you don't even want to be near those, near a generator that's bringing out those fumes. Yes, it usually has a choking effect, but it's basically an air pollutant. That's it. Some way it pollutes the air. That's the environmental effect. It's not anything positive. What does the scheme say?
Oh, it just says global warming. Global dimming.
It says what?
Global dimming.
Okay, so I didn't really hear what you said back there.
Global dimming.
Okay, blow it. Okay, okay. Mm, okay. Let me see if I picked it. But anyway, just hold on a minute. I still can't even annotate. Okay, go ahead. Go ahead. Let's move on to the next question. Okay, this one is about carbon monoxide. It says carbon monoxide may produce what? May be produced when the bonds. Okay, what does it now say? Give one reason why carbon monoxide is difficult. don't know. Can you hear me?
Sorry, I can't hear you. Can you say that again? Hello?
Okay. You have an idea why it says carbon monoxide is usually difficult to detect? I don't know. Can you hear me now?
Yes, I can hear you now.
Okay, all right. I asked, why do you think carbon monoxide may be difficult to detect? Let's say in a mixture of gases when it's produced by burning diesel.
Um, I don't. I should check on the.
So yeah, what did you say?
Are you asking for me to check the thing?
No. I was just saying, do you have an idea why it may be difficult to detect it?
Um, there's no color, right?
Okay, so it's colorless, but then something else is the fact that if you look at the chemical structure of carbon monoxide, it's actually CO, right? It's also, and then just imagine the difference between carbon monoxide and carbon dioxide. Carbon monoxide is CO, carbon dioxide is CO2. Did you see that? So the only difference between carbon monoxide and carbon dioxide is that carbon dioxide has an extra oxygen atom, okay, than carbon monoxide. Now imagine diesel produces carbon monoxide, and this is all going into the atmosphere, right? Remember, in that same atmosphere, you have oxygen already, isn't it? So
Uh,
what do you think will happen? The
um,
oxygen quickly combine with the carbon monoxide to produce what? Carbon dioxide. So it will be before you know it, the carbon monoxide has already turned to carbon dioxide, and it could happen so quickly, especially when it's going into the atmosphere. But let's see if the marking scheme says something different.
it says colorless or odorless.
Yes. Okay. It's colorless and it's odorless. Okay. Is that all it says? Hmm?
Yes.
Okay. So now let us look at it. These are the physical properties, right? If you really think about it, I think that's probably one of the reasons why um, carbon monoxide is actually dangerous, like really down to earth dangerous, especially if it's being produced in an enclosed space. It could easily suck up all the oxygen in that space, and if human beings are there, it means that they would easily choke, either start choking, you know, and it's been known to actually cause um, what do you call it, deaths, you know. For instance, nobody would want to start a car in a closed garage. You don't want to do that. Honestly, you don't want to, because the carbon monoxide coming from the car would, quickly take up all the oxygen in the garage, and nobody wants to be inside there without oxygen. It's more like suffocating. So yes, it's true. So it's colorless.
And
Did
it's
you stop
odorless.
sharing? Yes, and odorless. Yes. Okay, it's back now. Okay. All right. Okay, so it's just the physical properties they're interested in. That's fine. Okay, move on. Explain why water vapor and not liquid water is produced when diesel burns. Okay, so why do you think water vapor instead of liquid water? What I would say is because of the high temperature, isn't it? I mean, diesel is burning and it's definitely burning at a high temperature, right?
Yeah, yes.
Now imagine that high temperature is higher than the boiling point of water. So do you think water would be able to stay as water, liquid water, at that temperature?
No, no, no.
It won't. So it's just because it has exceeded the boiling point of water. So there's no way it would remain as liquid water. It would definitely be what? Water vapor. Okay. Okay, so that one is kind of a giveaway, more like but you need to carefully think it through before that may occur to you if you're not careful. Okay, let's move on. It says sulfur is a common impurity, and impurity, take note, it's not a desirable substance to have in diesel. So what does it say? Explain why this causes an environmental problem. Okay, so I'm not sure about this one. What does the marking scheme say? So we don't spend too much time on it.
It says sulfur dioxide is produced when diesel is burned, which which causes acid rain, which results in damage to buildings, statues, bridges, trees, and plants.
Okay, so they are kind of what do you call it? Harmful to trees and plants, right?
Yeah, yes.
Okay, 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 that's fine. Okay, all right, let's move on.
It keeps taking me off this.
Okay, I hope it's not from. Do you think it's from the internet connection?
I can't even tell because I don't know.
Okay, okay, let's just move on. Chromatography is used to separate mixtures. Okay, yes, it's a filtration technique. What does it say? And based on colors, it involves a mobile phase and one other phase. What is the other phase of in chromatography? So of course, from the word chroma, we know it has to do with colors. But let's see. Moving phase and it can be recycled phase. Doesn't make sense. I would go with stationary because after a while of moving, it has to stop. But yeah, it's stationary. I'll go with. What does it say for the marking scheme?
Yeah, it says stationary phase.
Okay, 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 okay. So of course we know how chromatography works basically. Remember the word chroma is means color. So it separates things based on their colors, their different colors, and the fact that they move at different speeds, and the fact that eventually after moving they would all stop at a particular point, and you'll be able to see them and tell, oh, this substance is in here, this other substance is in here, and so on and so forth. Okay, it says, why do the substances in the mixture separate in the mobile phase? Yeah, just basically what I said. They move at different speeds, right? They move at different speeds through materials like what the filter paper is made of. Okay, So if you look at experiments that have to do with chromatography, you will notice that the mixture is first put at the center of a filter paper that's been dipped in a liquid. Okay, so once it's dipped in that liquid and they put that substance at the middle, what will happen? That liquid, the substances inside the mixture will separate. Why? Because somehow they dissolve at different rates, speeds in that liquid that was used to soak the filter paper. So that's just the basic principle of chromatography. So if I were to give a reason why, I would say it's because the different substances in the mixture that we're trying to separate dissolve at different speeds, um, um, in the solvent that the filter paper is soaked in. But yes, I don't know if the marking scheme says something otherwise.
It says moves at a different speed, have different
Okay.
solubilities. Yeah.
Oh yes, abilities. Yes, exactly. That's what I was talking about when I said in the solvent that the filter paper is dipped in. Okay, that's all it says, right?
Yeah.
Okay, all right, that's fine. Okay, so I think pretty much covered it. Okay, let's see. Okay, what does the next question say now? Can you scroll up? Or scroll down rather. Okay. It says how many spots will be produced on the chromatogram of a pure compound? What do you think? If something is pure, right? What does that suggest to you?
That is zero spots.
Yeah, it doesn't have, there's no, I mean, it's a pure compound, so it doesn't, there's nothing else um, um, combined with it. So if you are saying how many, how
So
many,
one.
yes, I would go with one. Yes,
Yeah.
yes, it's just one. So the number of spots or the number of rings, because one ring will form, another ring will show how many compounds are in the mixture, because they will definitely expose themselves by moving at different speeds. Okay. Okay, I think we can go on to the next question. Okay. In a chromatography experiment, a blue color moved 4.77 centimeters. The solvent moved 5.30 centimeters. So the solvent moved further than the blue color, right? It says calculate the R value of the blue color. Okay. I'm thinking this has to do with some form of subtraction. But I'm not too sure. It's just basic subtraction. But what does it say with the marking scheme? What does it say?
R equals 4.77 divided by 5.30. I mean 30, sorry.
Okay, 5.30, right?
Oh yes.
Okay. 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 All right. That's it. Okay, let's move on. It says black ink is a mixture of several colors. True. True. Plan an experiment using paper chromatography to separate colors in black ink and identify the colors from their RR values. Okay, so I'm sure they will have some, some heavy details there. But if it's black ink that I know, black ink like in a biro, something like that. Number one, black ink would dissolve in a solvent like either kerosene or petrol, one of them. Okay, it usually dissolves only in organic solvent. Guess what? It won't dissolve in water. Water is a good solvent for things like salt. Yes, water is a good solvent for things like salt, but it would not work for things like black ink. Why? Because black ink is also an organic mixture. Okay, so it will only dissolve in organic solvents like petrol or kerosene. Okay, so but I think I would leave that one for you to just go through. Does it give details there? Does it give details there?
Yeah, it says near the bottom, draw a pencil line near the bottom edge of paper. Put a small black dot of ink on the pencil line.
Yes.
Put a small volume of water / surveillant in beaker. Place chromatography paper in solvent.
Okay.
Leave to run. Mark position of surveillant front. Remove the beaker. Leave to dry.
Okay. 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 Yeah. Okay. So yeah, that's basically how the experiment runs. I believe they will also give you the control measures to take so that you can get valid results, right?
Pardon?
Did they give you any control measures to take to ensure that you get accurate results?
Like extra. It says the dots of ink should be above the level of water.
Okay.
Support.
Okay.
Support the paper in this position. Put a lid on the beaker.
Okay.
Measure distance of all dots from start line. Measure distance of surveillant front from start line.
Okay. Okay. All right. Okay, I think it's okay. So I think if those are that's the essential, that's the core of the experiment, right? That's the core of what's expected in the experiment.
Oh yes.
Yeah. So the important thing to note is the fact that you need paper, filter paper, and you need a blot of ink, at a position where you clearly see the different components of that ink moving as a result of the soaking the filter paper in a solvent that ink can dissolve in. That's the basic concept of it. Okay. All right. I think we've been able to do 2 hours, but yeah. Do you think this is you can go further on this tonight? So we would look at a different subject tomorrow.
Oh, as in I should do chemistry. Yeah, I can do it myself. Yeah.
Okay. So we could do do you have a new one for maths?
A new what?
A new paper. That's a new one apart from the one. I know we did we finish the last one we were doing? The maths.
I'm pretty sure we finished the 3 that
Oh, okay. Okay. Could you check with your friend if he could give you another one? So we could use it tomorrow. Okay, so that's one possibility. Another possibility could be that we could take a look at physics. We could take a look at a physics paper, right?
Oh, okay. Yeah.
Yes, because so far we've done biology, we've done chemistry, so I don't think we've done physics. I know we've done maths, so we could do physics tomorrow or next. But either one, just see if he has a paper for foundation for physics and then one for maths, a new one for maths.
And yeah, okay.
Okay, so you let me know, right, on WhatsApp so we could plan towards tomorrow's class.
Okay, yeah, I will.
Okay, all right. Okay, I'll be expecting your message then.
So, should I try to send you the paper or?
No. You don't need to send me. Just let me know which ones he had, so that I'll know. Okay, so today, of course, I mean, well, by today I mean tomorrow. That's what I mean.
Okay, I will. Yeah.
Okay. All right. So I think we can call it a day for now. We'll see you again tomorrow by 6. I believe before then you'll be free. You'll be able to get the papers that we'll need for tomorrow's class. Okay. So is your timetable for your exams out?
Yes, it is.
Okay. All right. No problem. I guess your mom was saying that we'll be able to plan around it, possibly after tomorrow's class. Okay. Oh, you have a good evening.
Thank you. You too.
All right. Good night.
No.
Yeah, bye.